So here's another example that's a little bit more complicated, but the procedure is exactly the same. Instead of having a linear demand relationship as we did in a previous example, we now have a quadratic demand relationship. So the demand relationship that we have is that Q is equal to negative 2p squared plus 470,000. So what we're going to do is consider a price increase for an item from $98 each to $103 each, and then use the percent change formula to find the elasticity of demand in this situation. So if P is equal to $98, we can plug that into the demand function to find the quantity in demand. So negative 2 times the quantity 98 squared plus 470,000 can be computed very carefully using a calculator or spreadsheet. We have to be careful that we square the 98 first, multiply by negative 2 next, and then add 470,000. When we do that, we end up with a little over 450,000. So at a price of $98 each, there's 450,792 items in demand at that price. So of course that gives me a point on the demand curve just like we saw in the previous example. And now we just repeat that for the price of $103. We plug that into the demand function, carefully following the order of operations, and we end up with 448,782 items in demand at a price of $103. So again, a second point, and this allows me to do the percent change computations that I need to compute the elasticity value. So this slide should look very similar to one that we've already seen before. We're going to compute the percent change in the quantity in demand by looking at the new value, the new quantity in demand, which is just under 449,000, minus the original quantity in demand of 450,000 divided by the original value. And that gives me a value that is once again negative, but it's negative 0.004459. So if we convert this to a percentage, then we're looking at a situation where the quantity in demand is decreasing by about 0.4459%. So it's actually a relatively small decrease in demand. But what we want to do here is compare that to what the price increase was, so we can look at the ratio. So the negative value, as before, tells us about the fact that we have a decrease in demand. When we look at the percent change in the price, however, since the price is going up, the new value of 103 minus the original value of 98 is larger, so therefore we end up with a positive value for the percent change in the price. This is 0.051. So we're actually seeing a 5% increase in the price, but only seeing about 0.5% decrease or 0.44% decrease in the quantity in demand. So for a relatively large increase for the price, you're seeing the quantity in demand drop relatively slowly, so that when we look at the ratio, we're going to see a value that is much smaller than 1. So in this situation, when we take the absolute value, we end up with 0.087393 for the elasticity value. That's a pretty low elasticity value. It's much smaller than 1, and so elasticity here is inelastic. In other words, the quantity in demand is not very sensitive to price increases, and because of that, a price increase that's described in this situation should result in our total revenue going up. So those are a few examples of computing elasticity with a very basic percent change approach. There are actually several different other ways to compute elasticity with refinements to that formula that help give economists slightly more accurate measurements for elasticity. So there are things called midpoint calculations that can be done. So I'll leave that to a more advanced econ course or economics course that you might take that you can ask other professors about. But we're just going to focus on the really simple, straightforward approach that we just looked at here. But actually, what we want to do is make a transition to thinking about elasticity in terms of calculus, since we're in a calculus course. So we're going to make that transition here real soon. So the way we make the transition from percentage calculations into calculus-based calculations is with a concept that we call the growth rate. So if we want to figure out the elasticity at one single price, rather than looking at the elasticity as the price changes from one price to another, we use what we call the growth rate of a function. So we define the growth rate of a function to be as follows. The growth rate is simply defined to be the derivative of the function divided by the original function itself. So pretty straightforward. As long as you have a function, you can find the growth rate by taking the derivative and dividing in this way. So this is a way to measure the change of some function. Remember, the change of a function can be measured with the derivative. So we look at the change of the function relative to the original function itself. So this is sort of like percent change. Remember, percent change, you're looking at new minus old, so that's a change, divided by the old or the original. So you're comparing it to some original value. So the growth rate is very similar. You're looking at the rate or the change of a function measured by the derivative, defined by the original value of the function itself. So very similar. The big difference is that you're looking at a single point with the growth rate as opposed to 2 points, like we saw with the percent change calculations. So let's take a look at how this works. So the first example we're going to look at for growth rate is through a simple function. So we have a third degree function here that you can see here at the top of the slide, and we want to look at the growth rate of the function at a specific point, namely when x is equal to 2. So notice we're not saying let x go from 2 to 5 like we did with the price changes. This is the growth rate of a function at one single instant or one single point. So the growth rate is just the derivative of the function divided by the function itself. So when we calculate the derivative of this function, we know that the derivative of x cubed is 3x squared. The derivative of negative 3x squared is negative 6x, and the derivative of 4x is 4. Of course, the derivative of 8 is 0, but we don't have to write the 0 here. So that's the derivative of the original function f. We take that derivative, we divide it by the original function. So this ratio here that you see is simply an expression for the growth rate of the function f. Now, what we want to do is measure the growth rate when x is equal to 2. So all we're going to do here is plug in x equals 2 wherever we see an x. So when we do that, we get something that looks like this. So there's lots of arithmetic to be done here. It's not hard as long as you follow the order of operations, however. When we do that, we get the following. 3 times 2 squared is 12. Of course, negative 6 times 2 is negative 12, plus 4 on the top. So 12 minus 12 is 0. 0 plus 4 leaves me 4 up in the numerator. In the denominator, 2 cubed is 8. 3 times 2 squared is 12, or negative 12 in this situation. 4 times 2 is 8, and then we add the 8. So this gives me a total of 24 minus 12 in the bottom for a total of 12. So my ratio is 4 divided by 12, which simplifies to 1/3. So the growth rate of this function here is 1/3. Now, question becomes, when you look at this function 1/3, what does that really tell you? The growth rate is not a quantity that we typically measure in a traditional calculus course. It actually has more use in a situation like an econ or business situation where you can apply it. And where we're going to apply it is through elasticity of demand. So let's take a look at how growth rate can be applied to compute elasticity.